put that up. Wait, what's that?
Fashion Week in NYC. I like the Snapchat thing where you can see it. It gives me a glimpse of like the behind the scenes and the real thing when I can't actually see
It's
it.
recording right now.
I'm so sorry.
Yep.
Hi guys. Welcome to Physics with Mr. Kinsey.
What is it?
I said welcome to Physics with Mr. Kinsey.
Wait, how long is this gonna take?
Are you introducing me?
Yeah. Oh, sorry, I gotta stand up.
Make the introduction.
Hi everybody. Hello and welcome
What's your
to
name?
Physics with Mr. Kinsey. I'll be your host, Roseanne Hu, and soon I'll be introducing Mr. Kinsey.
This is the makeup lab for people who missed it.
Mr. Kinsey, you're supposed to walk in now. Mr. Kinsey?
He's setting him up.
I'm trying to get this.
Oh,
Yeah.
sorry.
Something-
Just wait a moment.
technical difficulty.
Who asked Peggy to prom?
What?
Somebody else making a room.
What? Holy crap.
Oh wait, JK.
That was probably Sarah Wong.
Oh really? Yeah, her snap?
Yeah, Sarah Wong.
Can you rewind it maybe? Yeah, a lot of people either. Everything's. I turned it off. Please below. So, is it on or off then?
It's on.
Alright, let's go. Speed. What the heck?
Okay, welcome to Rotation, Chapter 11. Basically, I said everything that we've done pretty much all so far in linear motion can be reproduced now in angular motion, or rotational motion. So the only difference is all the letters that we'll have will be Greek letters instead of regular letters. If we have a wheel, a bicycle wheel that's small and a bicycle wheel that's big, for like a tricycle maybe and a bicycle, then if we have them both going around at 1 revolution per minute, or maybe 1 revolution per second, and we put them on the ground, then the one that has a smaller radius is going to go slower than the one that has a bigger radius. So there's a nice relationship between the variables here. We have linear distance. It's r times the angular distance. You probably learned this in your pre-calc class as S equals r theta. So instead of D equals r theta. And then we have velocity is equal to r omega, and acceleration is equal to r alpha. And the basic idea is this column here is your linear quantities, and they're equal to the radius times the angular quantities. So linear quantities are equal to the radius times the angular quantities. This will be a little confusing later, which I'll point out something to you, but the main thing is the proportionality is the radius there. So linear distance, linear velocity, linear acceleration is equal to the radius times the angular distance, the angular velocity, and the angular acceleration. That's the first thing that we studied. In kinematics, we studied average velocity. So my average velocity now is going to be my average angular velocity, which will be omega. Sometimes it's a little bar over for omega average. And it's how far you went angularly, so the change in the theta divided by the change in the time. And our average angular acceleration, alpha, put the bar over average, is my change in omega divided by my change in time. That's the average. If we go to instantaneous, then this gets to our calculus part here. So we're going to go to instantaneous here. And we would say it's d theta dt and d omega dt. So the averages become instantaneous when you use differentials or derivatives there. So just like we had our 4 rules that we had before The slope of a distance time gives you the velocity, well, the slope of an angular distance time gives you the angular velocity, and the slope of a velocity time gives you the acceleration. The slope of an angular velocity gives you the angular acceleration. It's no big deal. And then we have the areas when you work backwards. You would take the area underneath the acceleration, angular acceleration versus time graph, and get the angular velocity, and the area underneath the angular velocity graph gives us the angular position. So it's all the same good old four rules that we had still work and apply here. We had, for constant acceleration, we had three major equations that we used all the time. And here's their rotational analogy. You may have recognized it. My angle final, theta final, is equal to my angle initial, theta initial, plus omega t plus 1/2 alpha t squared. That's where we had distance equals distance initial plus v initial t, omega initial t here, I forgot the initial, plus 1/2 alpha t squared. So all we're doing is changing it to, again, to Greek.
So wait, what equation is this?
Instead of d final equals d initial plus v initial t plus 1/2 at squared, this is
The angle.
theta final equals theta initial. Your final angular position as you're going around the circle.
Wait, what do you call this? Just like,
These are kinematics equations.
oh, this is the regular, okay.
Yeah, this is rotation. This is all kinematics. We start with, yeah. In physics, we're going to go through the whole chapters that we've done so far. And the first thing we study is usually kinematics. So we're not going to look at rotational kinematics, right, as opposed to translational kinematics. So everything here is just kinematics. The how of stuff, not the why yet. When we get into forces and stuff, then we'll talk about the why. Then your other equation that you had was omega final equals omega initial plus alpha t. That's like v final equals v initial plus at. And if you eliminate the time between these two equations, we had an equation that we liked that didn't have time in it, and it was omega final squared equals omega initial squared plus 2 alpha theta. Not mu alpha theta, but 2 alpha theta. That's the bad joke there for that. So these are the three equations that we use in kinematics, that we have the rotational analog there. I think that's pretty much all the kinematics equations that we have here. I have my cheat sheets that I took off from, we took the picture on last Tuesday. So I'm referring to my little cheat sheets, make sure I'm covering everything, so I'll do the same thing in each of the lectures. There is one other equation, I think, that that we had, as long as the acceleration is constant. Oh, by the way, these only work if alpha is constant. So in order for this to work right, that the angular acceleration has to be a constant. The one final one was omega average was also equal to theta initial plus theta final over 2. It's like your averaging numbers together. We had, for average velocity, it'd be your d1 plus d2 over the time. So it's the same thing we had before. No, I'm just thinking. Let me think here a second. I think that I may have written that wrong. Yeah, I think it's instead of omega average, it's really alpha average. Your average angular acceleration. Because your average angular velocity is the change in the distance. Well, gosh, I'm thinking about that there a second. Now I'm going.
Should be omega.
It should be omega.
I think it is omega, isn't it? Is it omega and
Omega.
omega averages initial plus final over 2,
Yes.
right?
Yes.
Initial position is always right and beforehand there. We'll leave it as omega average. There we go. Once we went through kinematics, then we went to dynamics. In dynamics, that's where we got to F equals ma. So we have torque equals I alpha, okay? The analysis, the analog here. So instead of A equals F over M, we now have alpha equals torque over moment of inertia. We've already studied in this class the torque equation of how to calculate torque. We did that at the very beginning of school. So, and where we learned that one, that the torque equation says R cross F. That's the vector way of doing it, or we learned it as R F sine theta. If we put the sine theta with the F, some people call it R times F perpendicular. If you put the sine theta with the F, okay? If we wrote it with the sine theta by the R, so we wrote R sine theta times F. And we put the sine theta with the R here, we had a special name for that, and that was called R perpendicular times F. If you remember, we did that one back in August and September. So this has a special name called the lever arm distance times the force. And here is just here we took all the R and the portion of component of the force, whereas here we took the component of the R and the total force. So it's the same idea, but we use those three different things interchangeably. And kinematics gives us the idea of for alpha, okay? But what we haven't looked at is what is this I thing, okay? So kinematics tells us, describes alpha. At the beginning of the school year we did torque, so we know that one. So the third one that we need to figure out is what in the world is this inertia thing, okay, rotational inertia. Well, it turns out that we have to be able to derive this in physics C. So first of all, let's come up with what the definition of moment inertia is. And in order to do that, the most common way of showing it is we have my axis here, and I'm going to have four objects. This one is R1 and M1, and this is R2, a different value than R1, and M2, a different mass than M1. And let's say here's maybe a short one, R3, but a big mass there or something, like M3. And then kind of back over here, maybe we got something maybe medium size. There's my R4, and my mass 4, could be a big one in there. And I'll put a little crank up here, and I'll start rotating this guy. So spinning it. There's the center right there. So I've got four particles that are spinning around, okay? And each of them has a certain velocity, and each of them has a certain mass. So it turns out that they each have a kinetic energy. So if I want to find the kinetic energy total of the system, so total kinetic energy, KE tot, I'm going to put TOT here for kinetic energy total. It's going to be, if I use the notation, the sum of, nice little Greek letter sigma here, from I equals 1 to capital N, where capital N is the number of particles that we have. In this case, our N would be 4 particles, okay? If we sum up the R sub I times, wait a second here. Let's look at it. Before I do this, let me rewrite it a different way. Let's write it a different way here. It's 1/2 mv squared plus 1/2 mv squared plus 1/2 mv squared, basically, okay? So basically, if I'm going to write it as 1/2 m1 v1 squared plus 1/2 m2 v2 squared plus dot 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 dot. Or the way we would do that, and then I'll use the little sigma notation I was talking about. So I'm going to have 1/2. Since all I'm having half out front, I'll put the half out front here. And then I'm going to talk about something from I equals 1 to n for 4 particles. It would be m sub I v sub I squared. So if I put the index of 1, I put an m1 v1 squared plus m2 v2 squared plus m3 v2 squared plus m4 v4 squared in this case. I'll put it that way. Well, how do I find Now what can I write as an expression for the velocity? Go back over here, we talked about the velocity is r omega over there. So if I substitute an r omega in here, so for v sub I, I'm going to put in r sub I times omega quantity squared. So there's my v equals r omega. Well, it turns out that however many rotations per minute or revolutions per minute that I'm going, or radians per minute that I want to call it, or radians per second, which is the usual angular velocity, it's the constant for everything. But the linear or tangential velocities for those particles are all different. So if I factor out this omega by itself, I'll pull it out over here, and this will come up with what we call 1/2 sum of I equals 1 to n again. And I got m sub I times r sub I squared times omega squared. So I pulled out my omega squared and right over here on the outside. And what I find here in this very middle part, the 1/2 is constant, the omega squared is a constant. I have this thing in the middle, and that's my definition of moment of inertia. Okay? It's how the mass is distributed about the axis of rotation. So moment of inertia is the sum of the m r squared.
I wasn't here during membership.
So I equals sum of m sub I r sub I squared. Oh, do we have questions? Y'all ask questions because they'd ask questions too. So
I don't know. I was just thinking, is it the same as this? I think I might have this during count.
So what we write is rotational kinetic energy is 1/2 I omega squared.
Rotational kinetic energy.
Yeah, that's KE rotational.
Is it this?
Yes, we're getting there. Yeah, we haven't got to the calculus version yet.
Okay.
Okay, in fact, you have the triple integral version. We're only going to do the single integral version. Okay. So I just want to tell you, in other words, we've talked about what the concept of the angular acceleration is. That's kinematics. We talked about torque at the beginning of the school year, but we haven't talked about moments of inertia yet. And so that's why I want to see where the definition comes from. The definition comes from the fact that if we're looking at kinetic energy particles and they're rotating around, then we have this new thing called the rotational inertia. Some people call it moment of inertia, and some people call it rotational inertia. I like rotational inertia better than moment of inertia because it's a little bit,
More descriptive?
yeah, a little bit more descriptive. If I gave you, let's see, I had a red and a blue card on the table over here. Looks like I moved it because I was getting the demonstrations up. So if I had my red and blue card, red card, my aluminum card, I'll grab it over here and be right back for you. And if I were to hand you these two cards, one's aluminum and one's plastic, and I ask you to tell me which one is the heaviest, you, by instinct, you sit here and go like this. You start trying to shake them usually, okay? So what you're doing is you're applying little forces to these things, and you're seeing how hard it is to resist the motion that you're doing to it. And the one that resists the motion the most, you'll say, oh, this is heavier, okay? Or, oh, this one's heavier, which it isn't. This is plastic, and this is metal, so it's much heavier. So that's the idea of inertia. We're applying forces, and we're trying to produce accelerations. Well, in rotation, we're applying torques, and we're trying to produce angular accelerations. So that's why I think calling it inertia and then sticking the word rotational in front of it makes a difference between inertia and inertia. So you got rotational inertia versus regular inertia. And somehow this moment of inertia kind of came up. And I think historically there's been some weird things. I remember some people trying to look it up one time and say, well, why do we call it that? And they came back the next day, one of the teachers that I was in a workshop, and they said evidently it has something to do with history. And how things get stuck there for a while, and they kind of get stuck there. Well, that's what they call the moment. And back to what they call the moment arm when we studied that over here with the torque. So they call it the moment of inertia. So I like rotational inertia better personally. So that's what I is by definition. Now, how do we get it, what's the calculus definition of inertia? Well, all your little sigmas, when you study calculus, become S's for sums of things, right? So the actual definition of moment inertia, calculus version of it, is the integral of r squared dm. Okay? That's mr squared, there's your r squared dm. Okay? And you're summing them all up.
With respect to omega, is that mass?
Pardon?
Like
This
where-
is r squared dm.
Yes, it's DM.
So the technique is going to be just like we did with Gauss's law, and we found out charge distributions. How is the charge spread around? Well, we're going to talk about mass distributions. How is the mass spread around? And that's why we're going to talk about something called moment inertia. Okay, and that's why we're using that. So just like in your Gauss's law, we studied lambda, we studied sigma, and we studied rho.
Roseanne.
So we have charge per unit length, we called it, Q over L. And we had charge per unit area, Q over A. And we had charge per unit volume, Q over V. Well, we can have the same thing with mass. We can have mass per unit length, mass per unit area, mass per unit volume. Those will be the same kind of what we call mass densities rather than charge densities. They're the same Greek letters. So here, that's the total mass divided by the total length. And here would be the total mass divided by the total area. And density would be the total mass divided by the total volume. So we're going to use the same little letters that you've seen before with lambda, sigma, and rho, as we talked about with Gauss's law. We're going to see we're using the same ones now with calculating moments of inertia, the way we just using some mass. Okay? So there's the first one that we're going to look at is, well, how do we do a ring? What's I for a ring? So you have just a regular ring,
1/2.
right? And we've got the mass distributed. It's all at the same distance away. So if I think about that, here's how we have to do it calculus-wise, and then we'll come back and say, well, what does all that really mean? Okay? So this ring has, if you look at it this way, it's got a length to it, a thickness. But an ideal one that we're talking about now would be one that's really, really skinny. So a very thin ring, okay? So if this is your ring, capital R is your radius, and capital M is your mass, your total mass, right? And we want to find the moment of inertia for that. And what we do is we take a small dm differential element of mass, okay, that occupies a certain ds arc length. That ds. Remember, S is the whole thing around the arc length,
And M is the mass.
and M is mass, right?
Okay.
So I'm taking the total mass, which is capital M, and I'm breaking it up into a bunch of little dm's. Okay? So a little dm1, dm2, dm3, dm4, all the way around. Okay? So you can already tell, if I did that over here, if I had all my r's were the same, and all my little dm's were the same, then I can already tell what I'm going to come up with. I'm going to come up with 1/2 mr squared. I'm just going to come out with mr squared here for that. And we'll show you what that comes out to over here. So, as I draw I've got the R there, I'm going to draw one right here too. If I look at this, which one of these charge distributions do you think is going to be nice to use for, basically it's a really thin wire. And instead of being a straight thin wire this way, we just made it into a circle. So it still has a what? A lambda, quote, mass distribution, a certain mass per unit length around it. So we're going to use lambda to be our total mass divided by our total length. In this case, what is the total length? 2 pi r, right? Well, the ratio of the total mass to the total length is also the ratio of the differential element of mass, dm, divided by my differential element of length, ds. So the dm divided by ds, the mass unit length here is the same as total mass over the total length, because we're saying it's uniformly distributed around the circle. We call it the ring. So when we do that, we solve this for dm, we get lambda ds. Okay, lambda ds. And with lambda ds, I can now put into my definition for I, and I come up with the integral of r squared, and I'm going to put in for dm lambda ds. Lambda is a constant, so I'm going to factor it out, right? And in your pre-cal you learned that s equals r theta, which is what we had over there, d equals r theta, so ds is going to be r d theta. So ds is going to be r d theta. So this little r radius vector here, okay? So if I put in here with r squared, lambda, and for ds, it's going to be r d theta. I'll pull out my lambda, I'll get r cubed d theta. Okay? And my r is the same thing, right? It's a constant, so I can pull it out as well. I was going to pull it out at the same time, r cubed lambda. And then let's get the integral d theta. Well, what's the angle? I'm going to start over here and go over out to from 0 to pi. So my limit of integration will be from 0 to pi. So that comes out to be r cubed lambda times theta.
Wait, did you just pull out the R from the?
Yes, they're all the same. The ring is every one of these little DMs. All these DMs are the same distance away. This is a perfect ring, perfect circle.
Okay.
Okay. So I pulled out the r cubed, and I pulled out the lambda. So I basically have an integral from 0 to pi of d theta, which we already know is theta. And remember the upper limit minus the lower limit. What are we going to come up with? 2 pi? Yes?
Yes.
So when I substitute things back in, my moment of inertia for the ring then becomes what? R cubed times lambda times 2 pi.
Oh, okay.
Okay, so what's going to happen? Okay, what's going to happen here? What is my lambda? My total mass divided by my total length, right? So my r cubed here, and my lambda is my total mass divided by my what? Total length, which is 2 pi r. And multiply by 2 pi, what's going to cancel?
2 pi.
2 pi.
The 2 pi is one of the r's. Make it 2 squared. And guess what? There's my r squared, yeah, or m r squared, which is what I already told you what it was over here, m r squared, right?
Right. You cancel out the r's.
Uh-huh.
When it
leaving
beats
an r
r.
squared. Do what?
It's already r's. Oh, is that r cubed? That's r cubed. Sorry.
Yeah, that's r cubed,
Yeah.
and then so when I take away one of the cubed ones, it becomes r squared. So I get m r squared. That's moment of inertia for a ring. We're just being real rigorous here to do it.
Yeah.
But I think you could have seen it over here with this first thing over here. If I drew my picture with all the little DMs the same distance around, right?
Yeah.
Then the total mass of that system would be m1 plus m2 plus m3 plus m4 plus whatever, blah, 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 right? And we get the same exact thing. And you would have to look at all the calculus. We need to get used to the calculus notation because that's what they're going to expect. So I think what we'll do is we need to derive a couple more moments of inertia. That's the most important part, and then we'll say that we're finished pretty much. because I promised off 4:15 and we're running already we started late, we're waiting for people to come.
He needs
By
to
the
go.
way,
I think I have to go
yeah,
soon.
by the way, we were supposed to have 6 people here and we had 3 show up, so I'm a little disappointed. So I don't know what we'll do. I guess I'll give the 3 that showed up here an easy quiz, and the 6 that didn't, the 7 that didn't show up, I'll give them a harder quiz that they'll have to do toward the end of it, okay? So, and if you need to run real quick already, since we told you that, then you need to run.
Okay.
We'll compromise with you,
Okay.
because we were waiting for you,
Yeah, I know.
okay? So, but what we want to do is I want to make sure I'm going to go to the camera and make sure we can zoom in to make sure we get all this before I erase it and start over here and work the moments of inertia.
Mr. Kinsey, did you mislabel an R? Is this?
Just a second, yeah, ask me while the video's going.
Okay, never mind. That looks like a 2 from far away. This
Yeah,
one.
that should be R cubed. It was R squared, but from the DS we got an R d theta, so we pulled another R over here. So
Right,
R
so-
squared times R became an R cubed.
And then you
And
pull
then
it
and
out.
I factored them all because they're nice.
Because they're not.
They're all the same.
Yeah.
And in fact, the little R and the big R are the same.
Right.
In my next derivation, don't stop it yet. You know, in the next derivation, the little R and the big R are going to mean something different. But in this case, since everything was at that same location all around, little R, big R didn't matter.
So
Same
it's gonna be
thing.
like the Gaussian
Right.
surface.
Pardon?
Gaussian surfaces where like R and the big R's are different.
Right, exactly. In fact, it's good, very good. Thanks for pointing that out. Because exactly what we did with the Gaussian stuff is what we're doing right here. Exactly the same thing. Okay, I'm gonna get out of the way and we're gonna make sure that we'll kind of pan through it and hold it for a little second. So
Yep.
you can make sure we can focus in on all the equations, okay? We need some little light music here, something going on.
Literally little night music.
Yeah, she knows. Now, they do some sight singing and solfege, Mr. Johnson, for your music theory.
Oh, true.
Is it so? Do so? I don't know.
No, it's do, so,
do.
yeah.
Do, so,
So-
do.
Alright,
Okay.
yeah.
And actually, we don't need this up here, because that's something that's gonna come in a little bit later. That's left over from today's lecture. So now we should have everything for when we're done. So we've got 2 derivations now for moments of inertia, and then we'll be finished. So hopefully we got all this basic kinematic stuff, and we're in the middle of dynamic stuff right now. And the most important one is what I was talking about, and spending the time, is how do I get these moments of inertia? Because that's the part that's hard, where we have to use the calculus to come up with the moment of inertia and deriving it from scratch. As 5th period saw today, the video that we found on the internet, the guy said, yeah, I can look it up in the table video time, I don't have to sit here and do it. Well, he's not going to take the physics C exam, because the physics C exam will make you, or they don't do it every year, but every other year or so, they'll make you derive it from scratch. So you do need to know how to derive it. So that's why we're making sure that you do that. And that's the part that's really tricky a little bit. So that's why I wanted to do that for the lecture. Okay? So here we go. Let's erase everything. And we're going to go from a cylinder, from a ring to a cylinder.